のハードロック聞いたら、金町まで歩いてバス路線をまた一つ見つけました。ハードロックにも押し上げ効果があるというね。やっぱパワーをもらえるんですね、あれも薬のようなもんだ。ヘビーメタルは音楽じゃないかもしれないですけど、あれはもうパワー薬みたいな、栄養剤みたいな感じですよ。新しい路線を見つけてしまいました。ありがたいという。またハードロックのファンになりそうですね。違うわ、こっちや。中川橋通らんといかん。ここにあるんだ。新宿なんだ。停留所がある。
Was simply a second piece of data, which I don't know if origin. It actually happens to be the derivative of the first piece of data. Okay, so I consider my CDR function instead of considering it as one function, I consider it as two functions, f and f prime. Okay, and I don't assume origin f prime has anything to do with that. It's just two functions. So that the second one is held over together minus 1. And then what about the first one? Well, the natural thing here is to assume that f of 1 is f of x minus f prime of x times 1 is x is the order of 1 of x to the gamma. And that in particular actually enforces f prime to be the derivative of f. Right, because, well, that's the definition of derivative, if it defines. So, now, instead of writing this as a pair f prime, I can just as well write it since any pair of functions is the same as a function with values in R2, and then I can give any name to the basis vectors of R2, and so I call my basis vectors of R2 purple 1 and purple x. And so this suggests that, well, purple 1 is the thing in front of purple 1 is the coefficient of the constant part of the Taylor expansion at that point, and the coefficient in front of purple x is the coefficient from the linear part of the Taylor expansion. Right? So functions in C2 are the same as functions of the form the left has purple 1 plus the left prime has purple x, where the left and the left prime satisfy this all the time. Okay? So just a rewriting of the usual definitions. And now you notice that this R2 with basis vector purple 1 purple x also, calling it purple 1 very much suggests that you will have a product for which purple 1 is the neutral element. Right? So you can put a product here where purple 1 multiplied with anything. Doesn't change that thing, and purple x has purple x has just been positively 0 because I don't have any other natural candidate here. Well, and now you see that magically, if you impose that rule and you write things like that, then the Leibniz rule actually just becomes normal multiplications. Right? So now you have two functions, capital F and capital G, and I just multiply them first. Right? So now it's not just that I've rewritten CCR minus a different way, I've written in a very, very natural way, in which the product is again just the product. Okay, even though the paper always looks like sort of pairs of functions, so that's not clear how we should multiply them, but if we write it in that way, it becomes absolutely clear how we should actually multiply them. It automatically gives you the Leibniz rule, and it automatically satisfies the product of CCR functions of CCR again. And you also know that these guys naturally come with a degree. Okay, so the degree of purple 1 is 0, and the degree of purple x is 1, and why should the degree of purple 1 be 0 and the degree of purple x be 1? It's really because, well, the purple 1, if you look at the actual, so the coefficients in 1 are the coefficients of the Taylor expansion on that point. So that means that these purple x equals the linear Taylor monomial, which will behave like this is 2 times to the power 1. That one should have degree 1. Now, so this is what I just said, right? So you have a natural also some kind of valuation, if you want. So for every point x, you have a linear map pi x, which takes as an input now the vector space spanned by purple 1 and purple x, and gives you the corresponding Taylor polynomial base at the point x. Okay, so pi x of purple 1 is just the constant function 1, and pi x of purple x is the linear function instead minus x. Okay, so with this notation here, now, if you have a C gamma function capital F, if you want the Taylor expand, if you want the Taylor polynomial of f at x, it's just pi x f of x. So here, pi x f of x is the function. It's the function z maps to f of x plus f pi of x times z minus x. And you notice here that, well, first these pi x's, if you vary the base point of your Taylor monomials, then you can actually implement this by just reshuffling the coefficients of the Taylor polynomial. Okay, so in other words, for any 2 points x and y, you have a linear map gamma xy that goes from the linear span of purple 1 and purple x into the linear span of purple 1 and purple x, and we set the property that pi y is pi x composed of gamma xy. And it is, it's very explicit, it's just this map here. Okay, so if you take this linear map, you take this definition of the pi x, it's obviously this identity here. Okay. And so now, with these notations, so remember, so here on the previous slide, so I had my definition of C gamma was these pairs of functions, with this norm here, and so this didn't look very systematic. So somehow I had something that looked quite different for f prime than for f. Okay, but actually, now with these notations, we have a very natural, nice way of writing this norm, so you can convince yourself that this here is exactly the same as what it was on the previous slide. Because what does this mean? So here, when I write, so here these are elements in the linear span of purple 1 and purple x, and when I write sort of norm beta, it means that it's the coefficient in front of the term of degree beta. So beta equals 0 is the coefficient in front of purple 1, and beta equals 1 is the coefficient in front of purple x. Okay. And so now for beta equal 1, well, what you see is that you see, so the gamma xy, it never changes what's in front of x. It only changes what's in front of y. Okay. So for beta equal 1, the gamma xy essentially is as if it didn't exist. And what you have here is just the little left hand of x minus the left hand of y divided by x minus y to the gamma minus 1. And that was exactly the first term, which is relative to C gamma minus 1. And then for beta equals 0, well, there you note that this gamma xy, the definition here, is exactly such that it creates this additional term here. Okay, and so for beta equals 0 here, you get exactly the second half of the definition of what it means to be C gamma. So now here, there's absolutely nothing new here, right? It's the old definition of C gamma going back to I don't know how long. It's just rewritten in a neat way, and it's written in a neat way that somehow doesn't really make reference to much anymore. Right? So here now you can kind of start to see how you would want to generalize this. Right? Because here now nothing else, so that, for example, immediately generalizes to C gamma not just between 1 and 2, but between, any integers. Right? So what you have to do is you have to add a purple x square and purple x cube, etc. The product rules are still the usual product rules. The gamma is just the thing that basically turns x into x plus x minus y1, and then it's you want it to basically be amorphous, so you want gamma of x squared and gamma of x and gamma of x, etc. So then that determines this uniquely, and that gives you the correct definition. And then you use exactly the same definition here, and you get C gamma for every gamma. But now, so say, well, okay, that's going to introduce other symbols. I don't have only this purple 1, purple x, and so on. So I just start throwing new symbols in, but mean different things, and then have different product rules. So nothing here forced these symbols to have anything to do with polynomials, and nothing here forced the product rules to be the normal product rules. Nothing forced this gamma to be, something around of the type polynomial of x minus y or anything like that. So what you can do here is now you can say, well, okay, so instead of having linear span of purple 1 and purple x, you have any sort of graded vector space. So the thing you should have in mind here is linear span of purple 1 purple x, purple x squared, things like that. So now you could have things of arbitrary degree, and the degree doesn't need to be an integer, and it doesn't even need to be positive. Okay? So I allow for things of negative degree, and I allow for things of fractional degree. The only thing I want is that the degrees still somewhat behave like the degrees of polynomials in the sense that there is a lowest degree, and you don't have accumulation points for degrees that look discrete, so you can still do induction with the degree. And then you want, so you want every guy in some vector space to represent some sort of Taylor monomial. And so before, so you want these last pi x that take purple x or purple 1 and split out the actual function that they're supposed to represent in the Taylor's function. And so you have a linear map that takes an element of t and gives out, well, in general, it's based on the distribution. Because you want things of negative degree, so you want to represent things like this white noise or stuff like that. And so you don't want to be restricted to just splitting out functions, you want to be able to split out distributions. Okay, so here the pi x is a family of linear maps from t into distributions, but you want them to behave near x in a way which is consistent with the notion of degree that we have here. So if you take a triangle degree alpha, okay, so if you take a t tau opposite, that means if you take tau homogeneous, meaning that it's actually one of the t alphas for a fixed alpha, and then I write this absolute value for the alpha in which it belongs to, okay, so it's degree. Then you would want that if you take this distribution, and now you see, so earlier I mentioned, well, the reason why purple 1 is degree 0 is because the constant function behaves like y minus x to the power 0. So here these things are distributions, so you cannot just evaluate them at a point and say, well, the thing should be less than y minus x to the power of the degree, because that doesn't make any sense. The best you can do for distributions is that you test it against some localized test functions. So what you do is you take a test function like this, you localize it at scale lambda, you scale it in such a way that scales like a delta function, and then you test against this. And so if it's a monomial, which is homogeneous of degree whatever k, and you test it against a function like this, you get exactly lambda to the k times the constant. And therefore that's exactly what you want to impose. So that's how you sort of relate the algebraic notion of degree here with some actual analytical bound. And then what you want is you want these gamma xy's that transform, that allow you to sort of change the value of x. Okay? And so this is the only property that we're going to use, is that they're group of linear operators on T, which has a similar property to the gammas here, which is that, it doesn't actually, it's always gamma of something, is always of the form that something plus stuff of lower order. Okay? That's exactly what you get when you change the base point of a monomial. Right? So if you have the monomial x to the k, you turn it into x minus h to the k, you expand that, well, you get x to the k plus stuff of lower order. Okay, and so you want these gammas to have exactly the same form. So gamma of tau is always of the form tau plus something which belongs to the, to the direct sum of the T alphas of degree less than alpha. The T betas of degree less than alpha. And then so you have this group of linear operators, and you want, connection gamma x5, which is exactly the property that we had before. And then again, we want it to be, we want this gamma x5 to have some analytical bound, which is compatible with our notion of degree. And what's the right compatibility condition here? So I explained that it's this. So in the sense that if you take the guy of degree alpha, you hit it with this gamma xy, and you look at the components of degree beta, beta has to be less than alpha because of the property of these gammas. Then we want to have a bound which is of the order of the distance between the two points x and y to the power alpha minus beta, so it's the power difference of degrees. Because that's exactly what you have when you expand a monomial, right? So if you take x minus h cubed, so you get x cubed minus 3hx squared, etc. And then you see that the term in front of the coefficient of degree 2 is of order distance to the power 1, and this 1 is really 3 minus 2. Okay, in the sense that the next term is going to be 3h squared x, and this 2 here is really 3 minus 1, etc. So this is, so I'm going to call this the regularity structure. So regularity structure is just these two objects. So that's like the algebraic part of these objects. And then the analytical part, which is this collection of linear mass pi and the collection of operators gamma, that's why I call a model. Okay, so for all of these equations now, what's going to happen is that first you build one of these regularity structures. So this you build it out of the sort of formal form of the equation. Okay, so you just look at what kind of operations appear in making sense of the right side of the equation, and that's going to determine one of these algebraic structures. But then you're going to take, well, you're going to build random models from the noise. Okay, so the algebraic part is going to be fixed, but the model, i.e. sort of these linear mass pi and the linear mass gamma xy, these are going to be random themselves, so they're going to vary depending on the realization of the noise. Okay. So now, you see, so now we have this natural sort of generalization, and of course, within this framework, this definition of C gamma still makes perfect sense. Right? So these are now just functions with values in this vector space, and which satisfy exactly this bound here, except that here you take the supremum over all the degrees less the gamma. Okay, so you only look at degrees less the gamma, and you take this definition here. And this still makes perfect sense. But now there's a very basic question. Right? So you have this notion of a kind of C gamma function or distribution. Now this capital F is a perfectly nice this function. But now what does this function actually represent? Right? So before, remember what happens is that for every point x, we could look at the pi x f of x, and that was simply the Taylor polynomial based on x for x, so on order, whatever the regularity of f is. Okay. So now this here still makes perfect sense, okay, because we have this continuous function capital F that takes values in this vector space, and we have this collection of linear maps, so for every element of this vector space gives a distribution, and so now for every point x, we still have this pi x capital F of x, which is some distribution on whatever our angular work on. Okay. So now for every point we're given a distribution. And now the question is, well, if this whole thing is going to be useful, then the first question we have to address is, when is there actually one single distribution, which does indeed near every point look like that distribution pi x f of x. So near the point x, it should look like the distribution pi x capital F of x. So that's the first theorem, which basically says that this always exists and is unique. Okay, so I define this D gamma exactly like C gamma. Okay, I just call it D gamma in order to remind myself that it's not the usual C gamma. Okay, but it's exactly the same definition as before. And now at every point x, we have this distribution pi x f of x. And the theorem is that for every so for every gamma in R, you always have this map, which takes one of these capital F, and it takes as input more than, it takes as input the capital F, and it also takes as an input the pair pi and gamma. It needs to know, but it needs to be able to figure out what is pi x f of x. So it takes both of these guys as an input, and it spits out the distribution, and the distribution that spits out, which is from Rf, has the property that if you take any x, and you compare Rf with pi x f of x, and then you get a difference of the distributions, so you cannot evaluate it, but you can still test it against test function. You test again against one of these localized test functions, the thing that you get is the overlap with the gamma. The gamma being that gamma up here. And this is true. This is a non-trivial statement even if gamma is negative, right? Because you see, since you allow negative degree, the most negative degree could be even more negative than the gamma, so you could still have things of degree less than gamma even if gamma is negative, right? So this definition is non-empty if you want, also if gamma is negative, and even if gamma is negative, that theorem is still true, but then it's just an existence theorem, whereas if gamma is positive, there's also a unique statement. The uniqueness function is trivial. I mean, we sort of see from this definition that if there is one such Rf, there can only be one. That's very crucial. And this is something true that actually exists. Okay. Now, it might happen, and actually so in the example that we're interested in, what's going to happen is that you're going to first fix this one from epsilon, and then fix epsilon, you're going to try to describe the solutions of an element in these spaces, and the whole point is that you want to estimate the unit of s, and we're trying to get s equals to 0. So now we'll fix epsilon, even though some of our things have negative degree epsilon, and you fix epsilon on the distribution, it will actually be continuous functions. Based on 6 epsilon, our x's will actually be continuous functions. And if you don't have a continuous function, then well, it's actually quite easy to convince yourself that Rf of x has to be pi s f of x equals to x. You can describe it. Okay, so the definition here doesn't make sense. modify it, you have to give yourself a product. So say you have a product C. And there's two conditions that you want for product. The first one is that, the degree of a product should be the sum of the degrees of the product. And the second one, here, is a bit less obvious, should be that every element in this group of operations, G, which do this re-expansion around a different point, should have the property that if you apply it to a product, it's the same as applying it to the individual factors and then multiplying. And this is very natural if you think of polynomial integration. So, you have a polynomial based at a point, and then you re-expand it around a different point. Then that's the same as the actual polynomial based at a point. You multiply them, then you re-expand around a different point. And that's the same as first re-expanding around a point, then multiplying. So it's the same operation. And so this is something that you want to post, which is really natural, because of what I just said. And if you do that, then it comes out that if you have if you have an F1 and it's gamma 1, if you have an F2 and gamma 2, if you multiply them, then it's again equal to gamma thing. And it's actually not in general gamma equal to this. Normally for the usual hyperpath, you are not thinking less regular. So here in general, you actually think of something even slightly less regular. So what you have to do is you have to look at what's the thing of lowest degree that appears in the description of each of these F5s. Yeah? And then you look at gamma 1 plus the thing of lowest degree appearing in the description of F2, minimum gamma 2 plus the thing of lowest degree appearing in the description of F1. But which is again sort of, it's not surprising at all actually, because it just says that, multiplying with something of negative degree is a little bit like taking some kind of fractional derivative, so you lose regularity in general.
So Sunday
and you have exactly that. So it turns out that the police have something or something they have to do. The thing is that you need then for every element in the vector space T, you need some kind of thing about I, which somehow represents the convolution of that element with in some sense. Because then it's something you can actually build. So if you have this, so you need certain algebraic structure on the space T, and then you actually need those ability condition on this high axis and the gamma x lots. Okay, so there's essentially a formula that tells you how the high x should act on these elements here, even as you know on itself. But assuming that you have that, then the theorem is that you can actually build a linear operator that includes regularity by 2. So that's e gamma, so e gamma plus 2. And which has the property that it really represents convolution with the heat kernel in the sense that if you take a guy in e gamma, you act with this operator, and then you apply this frequent flux operator, so you look at the actual distribution that it represents. So then that's exactly the same as the first working of which distribution represents. And as you see here, and furthermore that operator is actually off the form, simply applying that linear map, pointwise, plus our stuff. The difficulty to know, for the purpose of this lecture, is that the other stuff is going to only involve elements that are proportional to the usual thing elements. Okay, so in this part you actually need